Welcome to the Code Navigators. Our mission, well, it's pretty simple. We're here to guide you through the often very complex world of the International Code Council books.
We take a chapter, break it down, and really try to explain the dense stuff.
Exactly. We want to give you the navigation strategies you need to study for your ICC exams and, really get a quick, solid understanding of these building safety standards.
And today we're charting a course through a big one, Chapter 12 of the 2021 International Building Code.
Right. And just a quick note before we jump in about how we put this all together. We do use AI to help with the content generation, but then every single bit of it is produced and carefully overseen by a human code professional.
That's how we make sure we're delivering accuracy and, stuff that's actually relevant for your studies.
Okay, but before we get into the weeds, there's the legal stuff we have to cover.
Yes, absolutely. It's really important for everyone listening to understand. This program, the Code Navigators, it's for educational purposes only. Think of it as a study guide, a conversation to help you prepare.
So this is not professional advice.
Not at all.
Yeah.
It's not engineering consultation. It's not design services. We are just descriptively talking about the concepts that you'll find in the source material. We are not stating or endorsing any copyrighted code material.
So for any actual real-world projects...
You must always, always consult the official current edition of the building code that's been adopted in your specific area. And of course, work with a qualified licensed professional.
Because that's where compliance and safety really come from, the actual source document.
Exactly. Okay, disclaimer done.
With that necessary guidance out of the way, let's jump into it.
Oh,
Chapter
great.
12 of the 2021 IBC, Interior Environment.
I think this chapter might be one of the most important when you talk about the quality of life inside a building.
I would agree. It's everything that happens after the structure is up. It takes that building envelope you've so carefully designed and built and says, okay, now how does it actually have to perform for the people inside?
And the scope, which it lays out right there in section 1201.1, it's surprisingly broad. It really is. It covers ventilation, which is huge.
Temperature control, lighting, yards and courts.
Don't forget sound transmission between units. That's a massive one for occupant complaints.
Oh, absolutely. And then all the minimum dimensions for rooms, what materials you can use inside. If you're studying for an exam, this chapter is just a perfect example of how the IBC is like the central hub.
That's a great way to put it. It's a hub that points you out to all the other specialized codes.
Yeah, like the mechanical code, the energy code. It connects everything.
It's precisely right. Chapter 12 is really the checkpoint for habitability. If you don't meet these standards, you haven't just built something that's, technically non-compliant.
You've built a place that's just not good to be in.
Or even worse, a place that's potentially unhealthy, uncomfortable, or unsafe for the people using it. So I think the best way to tackle this is to break it down section by section.
That's good. Where do we start?
We start with the most fundamental thing for life, air. Section 1202, ventilation.
Right, let's do it.
So section 1202.1 kicks things off with the general ventilation requirements. And the very first thing the IBC does is it kind of defers jurisdiction.
It points you somewhere else.
Immediately. It says that for general ventilation, you have to comply with the International Mechanical Code. Specifically, it references IMC section 403.
And for certain buildings, it also loops in the International Energy Conservation Code, the IECC.
Right. And this is such a critical point for anyone navigating the code for an exam. When Chapter 12 says, go check the IMC, what it really means is that the actual nitty-gritty requirements like how many cubic feet per minute of fresh air you need or how to design the duct system, all of that lives in the mechanical code.
That the IBC is still holding you accountable.
Yes. The IBC is the one making sure it happens. It forces you to keep that whole family of codes in view. You can't just live in one book.
So the IMC is the specialized manual for air, but the IDC sets the overall context.
Exactly. The logic is efficiency. Now, where the IBC does get very prescriptive is on the tightness of the building envelope itself, especially for dwelling units.
And this is where we get to that one number that everyone has to know.
The absolutely vital number in section 1202.1 about air infiltration.
Okay, let's unpack this one because it's a core metric. For dwelling units, the code says the air exchange rate cannot be more than 0.4 air changes per hour, ACH.
And that's measured during a very specific test.
The blower door test, right. They pressurize the house to 0.2 inches of water column, which is the same as 50 pascals.
That zero point 0.4 H number is really a cornerstone of the modern energy code. It's pulled right out of the IECC. And just to make that number real for you, 50 pascals isn't some crazy amount of pressure.
It's not like a hurricane.
No, not at all. It's basically the same pressure as a steady 20-mile-per-hour wind hitting all sides of your house at the same time.
So what the code is doing here is not just measuring air loss, it's actually demanding a really high level of air tightness. If your house leaks more than that zero point 0.4 H, you are just hemorrhaging conditioned air.
Massive energy waste.
Yeah.
And you're almost certainly going to fail your IECC inspection.
Right.
And, it's more than just energy. The building science behind it is fascinating. If a building is looser than 0.4 H, what that tells us is the structure is probably getting its fresh air from accidental leaks.
Which sounds natural, but it's not good.
It's really not. Those random leaks are pulling air through your wall cavities, from your attic, from the crawl space. You're breathing in dust, insulation fibers, moisture, contaminants.
Whatever is lurking in your walls.
Exactly. But a tightly sealed building, one that meets that 0.4 H standard, it forces you to have a mechanical ventilation system. It makes you breathe air that's been intentionally brought in, filtered, and conditioned by your HVAC system. It's a huge health benefit.
So the tighter the envelope, the more critical the mechanical ventilation becomes. Build tight, ventilate right.
That's the mantra. And the code confirms it. Section 1202.1 says your mechanical ventilation has to comply with specific sections of the IECC and the IMC. It locks it all together. Once you seal it up, you have to ventilate it properly.
And this mandatory ventilation, it's not just for houses, right?
No, it extends to all occupied spaces within buildings. It's a baseline for health and safety. The code then specifically calls out accessory facilities and two occupancy groups in particular. Group R, which is residential.
Then group I2.
Group I2, right. Institutional occupancies like hospitals, nursing homes. It says they have to comply with their own specific sections of the IMC, referencing Section 407.
And that makes perfect sense. In our homes, Group R, we spend most of our time there, so we need good air.
And in I2, you have vulnerable populations, people who can't just get up and leave the building. So robust mechanical ventilation becomes non-negotiable for things like infection control and just general safety.
It's really where the life safety function of Chapter 12 directly connects with the health side of the mechanical code.
A perfect intersection.
Okay, so that's the big picture on building tightness. Now we shift from the whole building to a component that, if it's done wrong, it causes enormous headaches.
The roof assembly.
The roof, Section 1202.2, enclosed attic and rafter spaces. And the name of the game here is moisture control.
It's all about moisture. The requirement is very straightforward. You have to provide cross-ventilation for all enclosed attic and rafter spaces. Basically, any space between the ceiling and the roof.
You need air moving.
You need air moving up and out. You have to prevent moisture from building up. And that moisture, it can come from inside the house, from cooking, showers, just migrating up.
Or from a roof leak.
Or a roof leak. If that moisture gets trapped, it's going to condense on the cold roof sheathing in the winter. And then you've got mold, mildew, and eventually structural rot.
And to make sure that happens, the code gives us a calculation. This is a crucial navigation point for any exam. The net-free ventilating area calculation.
Yep. The standard requirement is a ratio. It's 1 to 150. You need 1 square foot of net-free vent area for every 150 square feet of the attic area you're trying to ventilate.
So, quick math. If you have a 1,500 square foot attic,
you need 10 square feet of net-free ventilation area. And it has to be placed strategically to get that cross-flow.
That 1 to 150 ratio is the baseline. It's the standard way to do it. But this is the building code, so of course there are other ways.
There's always an alternative compliance path. And this is the famous L/300 exception, or the 1 to 300 exception.
Which lets you reduce that calculation.
Exactly. It reduces the required vent area down to 1 to 300. But it's a signal. It means you've done something extra to help manage that moisture.
Okay, so let's break down how you qualify for that reduction, because it points to two very different ways of building. First thing, you always have to follow the manufacturer's installation instructions for the roofing and the vents.
That's a given. Then you have to satisfy one of two conditions, just one.
Condition 1.
Condition 1 is all about the geometry of where you place the vents. It allows the 1 to 300 ratio if at least 50% of your vent area is in the upper part of the attic.
Like a ridge vent.
A ridge vent or gable vent. And critically, those upper vents have to be at least 3 feet vertically above your eave or cornice vents. your soffit vents.
Okay, so what's the logic there?
I know.
Why the 3-foot separation?
It's all about the stack effect.
Yeah.
Hot air rises. By putting half your venting way up high and guaranteeing that vertical separation, you're creating a natural chimney.
So it pulls the air through more effectively.
Much more effectively. It maximizes that natural convection, which means you get faster air exchange, better moisture removal, and so the code says, okay, you can get away with a smaller total vent area.
Got it. So that's condition 1, smart geometry. What's condition 2?
Condition 2 shifts the focus entirely. It's not about airflow. It's about vapor control. And it specifically targets cold climates. It lets you use the 1 to 300 reduction only if you install a Class 1 or Class 2 vapor retarder on the warm and winter side of your ceiling assembly.
And this is only in climate zones 6, 7, and 8, the really cold places.
The coldest places, right.
We should probably clarify what those classes mean, Class 1 and Class 2 vapor retarders.
Good idea. In building science, we define them by their perm rating, which is just a measure of how easily water vapor can pass through a material.
So a Class 1 is like a sheet of plastic.
Exactly. It's considered impermeable. Plastic sheeting, foil-faced insulation. It has a perm rating of 0.1 or less. Basically, nothing gets through.
And a Class 2.
Class 2 is semi-impermeable. The rating is between 0.1 and 1.0 perms. It still stops a lot of vapor, but it's not a perfect seal.
So in those really cold climates, by making you install one of those, the code is essentially saying, what?
It's saying, look, we know the temperature difference between inside and outside is so extreme that condensation in the attic is almost guaranteed if moist air gets up there. So the strategy is to just stop the warm, moist indoor air from ever reaching the attic in the first place.
If you stop the source of the moisture,
You can rely less on ventilation to get rid of it.
that makes the two conditions crystal clear. One is about optimizing airflow. The other is about blocking moisture at the source in extreme cold.
Precisely. Now let's pivot, because the code does a big pivot right here. We go from venting attics to section 1202.3, unvented attic and enclosed rafter assemblies.
The hot roof design.
The hot roof. This is where modern high-performance building is going. You insulate right up at the roof line, creating a conditioned attic. You eliminate traditional venting altogether.
But if you go down that path, it's way more complex.
Oh, it's far more prescriptive. If you choose the unvented path, you have to meet some very strict criteria to make sure you don't trap moisture.
So condition 1 seems pretty straightforward. The unvented space has to be completely inside the building's thermal envelope.
Right. If you're heating and cooling the attic, it's part of the envelope. Simple.
Condition 2 is a don't.
A prohibition, yes. You are not allowed to install a Class 1 vapor retarder on the ceiling side, on the floor of the attic.
Why not? That seems counterintuitive.
Because the whole goal of many of these unvented assemblies is to allow drying in both directions, outward and inward. If you put a sheet of plastic on the attic floor, you could trap moisture that's trying to dry back into the conditioned space. You've cut off an escape route.
Ah, okay, that makes sense. And condition 3 is about specific roofing materials.
Wood shingles or shakes. If you use them, you have to separate them from the sheathing underneath with at least a 3/4 inch airspace.
Why?
Drainage and drying. Wood roofing needs to be able to dry out on its backside. That little air gap is crucial for its longevity.
Okay, this is where it gets really intense with the climate zone details. Sections 1202.3, .4, and .5, all about the type of insulation you use.
Right. This is all about condensation control, and it starts with air impermeable insulation. Think closed cell spray foam or rigid foam boards.
And again, this is for the cold climates, zones 5, 6, 7, and 8.
In those cold and very cold regions, you have to use a specific amount of this air impermeable insulation, and the entire goal is to keep the roof sheathing warm.
You're trying to keep the surface temperature of the wood above the dew point.
Exactly. You want to prevent the structural sheathing from ever getting cold enough for the moisture in the indoor air to condense on it, because if it does, you get instant condensation and mold.
And the code doesn't leave it to guesswork. It gives you a table.
Table 1202.3. This is an absolute must-know for exam prep. It links the minimum R value of that air impermeable insulation directly to the climate zone.
So for example, in zone 4B, which is kind of a temperate but still cold region,
The table tells you that you need a minimum of R15 of air impermeable insulation right up against the sheathing.
but then if you go way north to climate zone 8, like in Alaska or northern Minnesota,
The requirement jumps dramatically. You need a minimum of R35 of that air impermeable insulation.
wow, that's a huge difference.
It is, and it shows you how calculated the code's approach is. It's fighting condensation based on real-world average winter temperatures.
Okay, but what if you want to use something like fiberglass bats or cellulose, the fluffy stuff, air permeable insulation?
You can. Section 1202.3.5 allows it, but there's a catch. You can apply it directly to the underside of the sheathing, but only in combination with the air impermeable foam.
So you have to do both.
Essentially, yes. You use the closed-cell spray foam to meet the R value in that table to protect the sheathing from condensation. And then you can add the cheaper air-permeable insulation underneath it to get the rest of the way to your total required thermal performance.
There's another way to do it too, right? With insulation on the outside.
Yes, you can put sufficient rigid board insulation above the structural roof sheathing. But here, the rule is performance-based. You have to install enough insulation to keep the monthly average temperature of the underside of that sheathing above 45 degrees Fahrenheit during the 3 coldest months of the year.
So that's not a simple checklist item. That's a real design calculation you have to run.
It is. It requires a lot more work on the design side.
Now we have to flip to the complete opposite end of the country, the warm, humid climates.
Right. Requirements for vapor diffusion ports. This is for climate zones 1, 2, and 3. Here, the main worry isn't moisture from inside getting out and condensing in the winter.
It's summer.
It's summer, solar-driven moisture, and the need for the whole roof assembly to dry out quickly if it gets wet.
And the code gives 5 really detailed criteria for these ports. The first one is location.
The port has to be at or very near the highest point of the roof. No more than 12 inches down from the peak, measured vertically. It has to be right at the top to be effective.
Second is size, and it's another calculation.
Another ratio. The total area of the port has to be greater than or equal to the ceiling area divided by 500. It scales the port size with the roof size.
Third is the material, the membrane inside the port.
It has to be highly breathable. The code requires a vapor permeance rating of 20 perms or greater. This lets water vapor just fly right through it, but it's still an air barrier.
Which is the fourth point. It has to act as an air barrier between the attic and the outside. No uncontrolled airflow.
And finally, number 5, it has to be designed to keep rain and snow out. It has to be a weather barrier and a vapor release valve at the same time.
It's pretty incredible how Chapter 12 uses these completely different strategies for the same problem.
It really is. High airflow for temperate zones, heavy-duty vapor blockers for cold zones, and these super breathable ports for warm zones, all to achieve the exact same goal: stop moisture from wrecking the roof structure.
It just shows how much ventilation really depends on where you are.
Absolutely. Climate is everything,
Okay, so we've covered the roof, but moisture is just as big an enemy down below.
if not bigger. So Section 1202.4 takes us down into underfloor spaces and crawl spaces. They have to be controlled too.
And the traditional way to do that is with vents. Section 1202.4.1 says you need ventilation openings through your foundation walls for natural ventilation.
This is the old school method for keeping crawl spaces dry and, getting rid of any soil gases like radon that might build up.
And here we have another one of those key ratios for exams, the net free area rule for crawl spaces.
And it's the same ratio we saw for attics, 1 to 150. 1 square foot of vent area for every 150 square feet of crawl space area.
And you have to place them near the corners,
Right.
within 3 feet, right, to maximize that cross breeze.
Exactly. But what really stands out here and shows you the practical reality of building is how specific the code gets about what you cover those openings with.
Yeah, the list of materials is intense.
First, the opening itself has to be a decent size for air to move, at least 3 inches high and 7 inches wide.
And then the coverings. It's all about durability and keeping pests out.
Total focus on keeping rodents out. We're talking perforated metal plates. It says they have to be at least 0.070 inches thick, or expanded sheet metal, no less than 0.047 inches thick,
Or cast iron grills, extruded load-bearing vents.
or hardware cloth, but only if it's made with 0.35-inch diameter wire or heavier.
Why so specific? Why not just say use a screen?
Because a regular window screen will rust out in a year, or a squirrel can chew through it in 5 minutes. By mandating these thick, durable metal materials, the code is trying to ensure that the pest barrier lasts for the life of the building, not just for the first couple of seasons.
Makes sense. Then we have a special case in 1202.4.2, flood hazard areas.
Right. If your crawl space is in a designated flood hazard area, the openings have a different job. They have to comply with ASCE 24.
So they're not for ventilation anymore.
They become automatic flood vents. Their job is to let floodwater in and out freely to prevent hydrostatic pressure from building up and collapsing your foundation walls. A completely different function.
And then, like with attics, there are exceptions to the whole natural ventilation rule.
Of course, Section 1202.4.3 lays them out. You don't need vents for things like an enclosed porch or a dedicated data processing center that needs a controlled environment.
But the big one, and this is a really common design choice now, is the conditioned crawl space.
The conditioned crawl space, yes. In the colder climate zones 5 through 8, you don't need those foundation vents. If you condition the crawl space air according to the IMC and you insulate the foundation walls according to the IECC.
So you're basically turning the crawl space into a short basement.
That's the perfect analogy. You're shifting from a wet, cold, vented crawl space to a dry, warm, sealed one. You move the building's thermal boundary from the floor joists down to the foundation walls.
Which, from an energy standpoint, makes total sense. Why would you vent all your heated air to the outside?
You wouldn't. You've essentially just made the crawl space part of the house.
Okay, one last point on this section. Contaminated soil.
A critical health risk. Section 1202.5 says if you know the soil under the building has contaminants, maybe it's an old industrial site or an area with high radon, you can't just rely on passive vents.
You have to step it up.
You have to provide mechanical ventilation, again, in accordance with the IMC. You have to actively suck out those hazardous gases and vent them safely away from the building.
All right. So, Chapter 12 has shown us how to move air, keep moisture out of the roof, and keep the crawl space clean and dry. Now we get to pivot from all that structural performance stuff to the things occupants feel every day.
The immediate comfort and usability requirements, starting with temperature and light.
Yes. Section 1203, temperature control.
This one sets a very clear, very simple minimum standard for basic human comfort.
And the standard is 68 degrees Fahrenheit, or 20 degrees Celsius. Interior spaces for human occupancy have to have a system that can maintain that minimum temperature.
And the code is very specific about where you measure that 68 degrees.
Right, at a point 3 feet above the floor.
And that's not an arbitrary number. The reason is that heat rises. If you only measured up by the ceiling, it could be 72 degrees up there, but 55 down on the floor where people are actually living.
So measuring at 3 feet ensures comfort for someone standing or sitting. It's about performance, not just, how hard the furnace is working.
Exactly. Now, there are some pretty clear exceptions to this.
You don't have to heat every single space in a building.
No. Section 1203.1 lists them. Spaces that are intended for human occupancy or certain occupancy groups.
Like factories.
Group F for factory and industrial, Group H for high hazard, Group S for storage.
Or Group U for utility and miscellaneous. A barn, for example.
Right. If you're just storing boxes or running a specialized machine, the heating requirement might be waived.
Okay, that brings us to Section 1204. Lighting, another fundamental requirement.
Every space for human occupancy has to have adequate light. And you can do it one in two ways.
Natural light from windows or artificial light from fixtures.
For natural light, Section 1204.2 gives us another one of those classic code benchmarks, the 8% rule.
The net glazed area of your windows has to be at least 8% of the floor area of the room.
It's a long-standing rule of thumb to make sure you get enough daylight in a space to reduce the need for artificial light during the day.
But what if you have a room with no exterior walls, like an office in the middle of a building or a bedroom next to a sunroom?
That's where you get the adjacent room exception in 1204.2.1. It lets you borrow light from another room.
But you can't just have a tiny little window between them.
No, there are specific opening criteria. The opening between the two rooms has to be at least 25 square feet, and that part of that opening on the common wall has to be at least 10 square feet.
Those are two numbers that are really easy to mix up on an exam. 25 square feet total, 10 square feet on the common wall.
And they are critical. It ensures the pathway for light is actually meaningful, not just some tiny transom window over a door.
Okay, so if you don't have natural light, you need artificial. Section
Yeah.
1204.3.
And here, the requirement is 10 foot candles, 107 lux. And again, it specifies where to measure
Right.
at the floor and also at 30 inches above the floor.
And 10-foot candles, for context, is what?
It's roughly the amount of light you'd need to comfortably read a newspaper with large print. It's a general visibility level. But that dual measurement floor in 30 inches ensures the light is actually usable where people are doing things, not just concentrated in fixtures up on the ceiling.
Then the section gets into safety lighting.
Sections 1204.4 and point .5.
Hmm.
Mandatory lighting for stairways. You need at least 1-foot candle on the treads and risers.
And then, most critically, 1204.5 requires emergency egress lighting.
Which has to comply with Section 1008.1. This is the system that keeps the hallways and exit paths lit up during a power failure. It's a fundamental life safety element.
Okay, next up is a section that people might not think of as part of the interior environment. Section 1205, yards and courts.
But they are, especially when those yards and courts are what you're using to get that 8% natural light we just talked about.
Good point. So the minimum width is tied to the building's height.
Right. For buildings that are 2 stories or less, the yard or court has to be at least 3 feet wide.
But as the building gets taller,
The yard has to get wider. For buildings over 2 stories, you have to add 1 foot to the minimum width for each additional story, up to a maximum calculation based on 14 stories.
so why does it scale with height? What's the thinking there?
2 main reasons. First is light and air. The taller the walls around a courtyard, the less light and air can get down to the bottom floors. So you widen the court to compensate.
And the second reason?
Firefighting access. Imagine trying to get ladders and equipment into a narrow 3-foot wide courtyard at the base of a 6-story building. It's a safety and access issue.
And these yards and courts, they can't just be muddy pits.
No, Section 1205.3 covers access and drainage. They have to be graded properly and drained to a sewer or other approved system. You have to follow the International Plumbing Code. Prevents them from becoming big, unsanitary mosquito ponds.
All right, Section 1206. This is a huge quality of life issue. Sound transmission.
A perennial source of complaints from tenants in apartments and condos. This applies to the walls and floors that separate dwelling units from each other or from public spaces like hallways.
And the requirement here is very specific, very numeric. Perfect for an exam question.
The magic numbers are 50 and 50. The assembly has to have a minimum sound transmission class, or STC, rating of 50, and a minimum impact insulation class, or IPEM, rating of 50.
Let's quickly define those. STC is for airborne sound.
Voices, TV, music. An STC of 50 means that if someone is talking at a normal volume on the other side of the wall, it should be inaudible.
And IPEM is for impact noise.
Footsteps, furniture being moved, something being dropped on the floor above you. An II of 50 is considered the minimum for acceptable performance in multifamily housing.
And how do you prove you've met that 50-50 standard?
Well, you demonstrate compliance through lab testing. ASTM E90 for STC, ASTM E492 for IIs. Or you can use engineering analysis based on systems that have already been tested. But the point is, you have to do the calculation or the testing to prove it.
The real trick here, and where so many projects fail, is in the details.
100%. This requirement applies to the entire assembly, not just the drywall and studs. It includes every single penetration.
So all the outlets, the light switches, the plumbing pipes.
Every single one. You have to meticulously seal around every electrical box. You have to caulk the sill plates. If you have a beautifully designed STC C60 wall, but you put in back-to-back electrical boxes with no protection,
You've just created a perfect hole for sound to go right through.
you've created a speaker. And all that effort and money is wasted. This is where the workmanship on-site makes all the difference between a quiet, compliant building and one that generates nonstop complaints.
Okay, let's move on to the last major part of the chapter. We can skip 1207, which is super specific for classroom acoustics. Let's go to section 1208, interior space dimensions. This is what makes a space actually usable.
This is what dictates if a room is truly a room. Section 1208.1, habitable room size, sets the first rule.
Every habitable room has to have a minimum dimension of at least 7 feet in any direction.
And the code is clear that kitchens are excluded from this rule.
So why 7 feet?
It's about function. A 5-foot wide room, no matter how long it is basically a hallway. You can't furnish it properly, you can't really use it effectively. The 7-foot minimum prevents designers from creating these long, skinny, useless spaces and trying to pass them off as bedrooms.
Then in 1208.2, we get minimum ceiling heights.
For most habitable rooms, the ceiling has to be at least 7 feet 6 inches high.
7.6.
For at least half of the room's area. That height is mostly about comfort and making sure standard doors and windows fit properly. It keeps a space from feeling cramped and oppressive.
What about sloped ceilings, like in an attic room?
The code allows for that, but with limits. Any part of the room where the ceiling is less than 5 feet high cannot be counted toward your required minimum floor area.
And anything under 5 feet is basically just storage space anyway.
Exactly. It's considered unusable for habitation. The code also has a rule for furred ceilings, where you drop a section of the ceiling down to hide ductwork or lights,
That lowered part has to be at least 7 feet high.
with a small exception. If the total furred area is less than 7 square feet, you can go lower. It's a practical allowance for small utility chases.
Now we get to the actual minimum room area in 1208.3. Another set of numbers to memorize.
A very important set. In any dwelling unit, at least one habitable room has to be at least 120 square feet.
That's your main living space, your living room or maybe a large master bedroom.
Right. And then all the other habitable rooms, again, not counting the kitchen, have to be at least 70 square feet.
So 120 for the main room, 70 for the secondary bedrooms or dens.
The distinction is key. It allows for design flexibility. The primary social space needs to be a decent size, but the other rooms can be smaller as long as they still meet that 7-foot minimum dimension we talked about.
The chapter then has a special section, 1208.4, just for efficiency dwelling units.
Studio apartments, basically. Even though they're small, they still have minimums to ensure they're functional.
And that minimum floor area is 190 square feet.
190 square feet. It also has to have a separate bathroom and a clear kitchen working space of at least 30 inches. It's essentially the smallest legal apartment you can design under the IBC.
All right, moving on. Section 1209 is about getting into those unoccupied spaces.
Access. If you have them, you have to be able to get into them for maintenance and inspection. For crawl spaces, 1209.1 says the opening has to be at least 18 inches by 24 inches.
Just big enough for a person to get through.
Exactly. For attics, in 1209.2, the requirement is a little different. If the attic has more than 30 inches of headroom.
The opening needs to be bigger, 20 inches by 30 inches.
Right. And the reason it's larger is because attics often have equipment in them. Air handlers, big sections of ductwork. You need a bigger hole to move that stuff in and out. The crawl space is more about human access. The attic is about mechanical access.
That makes sense. Okay, we've reached the last section, section 1210, toilet and bathroom requirements.
This is all about the physical space and the materials you use for sanitation.
1210.1 just reminds us that the number of toilets and sinks you need is covered back in Chapter 29.
Right. Chapter 12 is just about the room itself. And
Yeah.
1210.2 sets some tough standards for the finished materials in wet areas
Walls have to have smooth, non-absorbent surfaces.
to make them easy to clean and to stop moisture from getting into the wall, which would cause mold and rot.
And there are exact dimensions for how far up the wall that material has to go.
The non-absorbent surface has to go up at least 4 feet above the floor, and it also has to extend 4 inches up from the floor to act as a base.
But for showers and tubs, it's even stricter.
Much stricter. Because of the constant water exposure, inside a shower or a tub enclosure, the non-absorbent walls had to go up to at least 6 feet above the floor.
And you need waterproof joints where the tub meets the wall.
Absolutely mandatory to keep water from seeping into that wall cavity.
The section then talks about privacy. 1210.2.1, water closet compartments.
You need stalls, basically, walls and partitions to separate the toilet from public view.
But there are exceptions.
Right. You don't need them in a single-occupant toilet room or in a private bathroom inside an apartment that's not open to the public.
And the same logic applies in 1210.3 for urinal partitions.
You need partitions between urinals in public or employee restrooms. And again, the dimensions are very specific to ensure privacy.
They have to start no more than 15 inches off the floor.
And they have to extend up to at least 60 inches, 5 feet above the floor.
That combination of the low start and the high top provides good privacy for the user, but it also leaves space for cleaning and maintenance.
It's a balance between privacy and practical facility management. And just like with the toilets, there are exceptions for single-user rooms or in certain daycare facilities. The code recognizes that the context and the user really matter.
Wow. Okay, that was a journey through IBC Chapter 12, from air leakage to urinal partitions. It really covers the whole interior environment.
It's an incredible amount of detail.
So to wrap it up, we covered those really strict air integrity rules, especially that 0.4 air changes per hour for dwelling units, and all the complex trade-offs for attic ventilation, like the 1 to 150 standard versus the 1 to 300 exception.
We hit the minimum quality of life standards. That 68-degree minimum temperature measured 3 feet off the floor, the 8% glazed area for natural light, and those critical STC 50 and ISC 50 ratings for sound.
And then all the dimensional rules. The 7-foot minimum dimension for habitable rooms, the 6-foot high non-absorbent finish in a shower. This chapter is just packed with numbers that are vital for anyone serious about building codes.
I think the real takeaway here is that Chapter 12 is less about the bones of the building and more about the human experience inside it.
It's about performance and comfort.
Exactly. Understanding why you need a certain R value for condensation control, or why the width of a courtyard has to scale with building height. That's the difference between just memorizing a number for a test and actually grasping a building science behind a successful project.
So what's the biggest challenge for someone studying this chapter?
I think it's connecting all these different topics, air, light, sound, size, back to that central theme of habitability and safety. Practice explaining the why behind the number. Why 7'6" ceilings? Why 50 pascals for the blower door test? If you can understand the rationale, the number itself will stick in your memory.
That's great advice. So if you found this structured analysis valuable for your own study and exam prep, you can support the Code Navigators.
We have a Patreon link in the show description. Your support helps us create future explorations of other chapters and content.
Your contribution really does help us continue to provide this kind of detailed, targeted guidance. Thank you for navigating the 2021 IBC Chapter 12 with us.
We'll see you on the next exploration of the Code Navigators.